In this video, we're going to talk about the rules of logic. We're looking to answer a few different questions, like how can we tell if two statements mean the same thing? How can we determine whether an argument is valid? And how can we simplify complicated logical statements? We're going to be using a mathematical tool known as a truth table in order to answer questions like this. Let's take a look at an example we might see in a linear algebra class. This consists of three statements, P, Q, and R, all relating to this matrix A. So statement P says A is invertible. Q says the system AX equals B has a unique solution for every B. And the statement R says the columns of A span Rn. We're not going to worry too much right now on whether or not we fully know all of the terminology within each of those statements, but actually we just want to kind of analyze a statement consisting of these statements, the statement below, which is if P then Q or if Q then R. And the question is this statement always valid? And so we're going to learn later in this video that a statement that is always valid is what's known as a tautology. So the question is this particular statement a tautology? This statement kind of made up of these parts P, Q, and R. If it is a tautology, then we've learned something about these different statements. So we'll learn how to use truth tables to determine if a statement is a tautology and then come back to this example later. Let's consider another example here, which has these two statements. If a matrix is invertible, then it has a non-zero determinant, and the determinant of matrix A is 0. The question is, what can we conclude about A? So, if a matrix is invertible, then it has a non-zero determinant, and then we are told that the determinant of matrix A is 0. So this first statement here has the form if P then Q, and the second statement, the determinant of the matrix A is 0. So it is, not non-zero. So not Q. What can we determine from this if we kind of think back to when an if-then statement is, going to be true under the condition that Q is false, we would have to have the fact that P is also not true, because if P were true and Q were false, then that statement, if P then Q, would be false. So what can we conclude about A? We can conclude that A is not invertible. So why should linear algebra students care about logic and these different forms and some of the things we're going to see in this video? Many theorems in mathematics, including in linear algebra, have the form if P then Q. Some examples you might see in a linear algebra class: if a matrix has a pivot in every row, then its columns span Rn. If a set contains more than n vectors in Rn, then the set is linearly dependent. If a matrix is invertible, then Ax equals B has a unique solution for every B. Understanding logic will help us understand what these statements actually mean and gives us the tools to prove them, which is ultimately going to be our goal. Let's talk about truth tables. So a truth table lists all possible truth values of the atomic statements and determines the truth value of a molecular statement. So if we have n atomic statements and we want to list all possible truth values and all combinations of the different truth values, then our table will have 2 to the n rows. So if we have 2 molecular statements, then our table will have 4 rows. If we have 3 molecular or atomic statements, then our table will have 8 rows. If we have 4, we need 16 rows, and so on. Here are some basic truth tables for some of our sort of basic molecular statements. So all of these just include either just P, as we see at the bottom, or P and Q together. And you could see, so, 2 statements for this example here means we have 1, 2, 3, 4 rows, which gives us all the possible combinations of P and Q being true or false. And so this is the truth table for the statement P and Q. And we may recall that this particular type of a statement is only going to be true when both P and Q are true. So we see that here, that P and Q is true precisely when both of these are true. Otherwise, P and Q is false. Coming over to P or Q, this one's true anytime either P or Q is true and only false when they are both false. So we see the false down here when they're both false, and the rest of these true when at least one of them is true. Coming to the if P then Q statement, this one is only false when P is false and Q is true, and we see that here. And then the P if and only if statement is going to be true when both statements are true or both statements are false. And we see that. And then finally, we have our negation. So not P is true when P is false and vice versa. So we see that not P is true when P is false and not P is false when P is true. It's going to be important to understand these sort of basic truth tables as we're developing some more complicated ones. So let's look at a more complicated one here. This consists of the statement, if P and Q, then P. So we have two atomic statements, therefore our table is going to consist of 4 rows. So we can sort of construct this here. We're going to have P, Q, and then our 4 rows. And so we want P to be true or false, and then Q to be true and false with each of those options. And then we want to construct the truth table for this P and if P and Q, then P. So we sort of break this down into some parts. We can have a P and Q part, and then we can have a P and Q, if P and Q, then P. So now we just go through. So P and Q, this is going to be true. And again, we can go back to sort of this basic one. This is true when both P and Q are true and false otherwise. So we've got true, false, false, false. And then the if P and Q, then P is going to be, coming back to our basic truth tables, false exactly when the sort of first part is true and the second part is false. The first part being the P and Q. So this is going to be, again, only false in the situation where P and Q is true and P is false. So let's see. Do we have any of those? P and Q is true in this first one here, but P is also true. So we have true, true. So that's fine. Otherwise, P and Q is false. So, the if P and Q, then P, I guess, is going to always be true. We don't have any of those true, that if true, then false possibilities. Okay. How can we use truth tables as proof tools? So truth tables allow us to answer questions such as, is a statement always true? That's what we saw earlier with this concept of well, that's what we're going to see in a few minutes with this concept of a tautology. We saw actually this example here. This statement is always true, so that's kind of interesting. Are two statements logically equivalent? And then is a deduction rule valid? In later sections, we will use these to justify proof techniques and mathematical arguments. So now to tautologies, a statement that is always true is called a tautology. Its truth table contains only t's in the final column. An example is P or not P, and actually another example was this one right here. We can see all t's in that final column. But let's run through this example here. It should be pretty quick. So we only need 2 rows because we just have the one statement. So P can be true or false. We want not P, which will go false, true. And then we want P or not P. And the or statement is true as long as one of the two statements is true. And we can see that is the case here. So we have true, true. Onto logical equivalence. So we say that two statements are logically equivalent if they have the same truth value under every assignment of truth values. And we would write P with this sort of, is logically equivalent to Q. We have this kind of triple equal sign type of a symbol for that. Equivalently, the final column of their truth tables are identical. So we can use truth tables to determine if two statements are logically equivalent. Suppose we know that P and Q are logically equivalent, then they always have the same truth value. So proving P proves Q, proving Q proves P, disproving P disproves Q, and disproving Q disproves P. So logical equivalence allows us to replace one statement with another that may be easier to understand or prove. And we're going to see that when we get more into our proof techniques in the next section. Let's try an example. Are the statements if P then Q and not P or Q logically equivalent? So let's build a truth table for this. So we need 4 rows again. Okay, so we'll do our true, true, false, false, and then true, false, true, false. And then we can have our if P then Q. And then we're going to want not P. And then we can have our not P or Q. So if P then Q, again, is only false when P is true and Q is false, which is here. Otherwise, it is true. Not P is going to be false when P is true and true when P is false. And then the or not P or Q is going to be true when either Q or not P is true. So true, false. You can see that both not P and Q are false in this case. So that's false, true, true. And now we want to compare the columns here and here. We could see they are identical, and therefore, yes, those two statements are logically equivalent. And so in order to prove an if P then Q statement, we might instead consider proving a not P or Q statement. And we'll see that a little bit later. Suppose we want to prove if P then Q. Some common approaches we're going to see in a later section are proving it directly. And we'll talk more about what each of these means, but direct proof, contrapositive proof, and proof by contradiction, understanding logical equivalence tells us when these methods are valid. Let's talk about contrapositives. So recall that if P then Q has the contrapositive, not Q then not P, if not Q then not P. And theorem 135 says that an implication is logically equivalent to its contrapositive. So if P then Q is equivalent to if not Q then not P. And we can prove that using a truth table. Again, we're going to need our 4 rows. You might get good at creating this if you do enough of them. Okay. All right. So if P then Q, again, is true, false, true, true, like that. And then I guess we want to not Q. We want to not P. And then we'll have our not Q. If not Q, then not P. So not Q is going to have false, true, false, true. Not P is going to have false, false, true, true. And then if not Q, then not P is only going to be false when not Q is false and not P, or excuse me, not Q is true and not P is false. So that's right here. no other rows. And so we can see that the if P then Q column exactly matches the if not Q then not P column. And so this tells us that these two statements are logically equivalent. And if we wanted to prove one of them, we could instead prove the other one. And this is going to lead to a really useful and common proof technique known as a proof by contrapositive. So an example you might see in a linear algebra class, suppose we had statement P says a set of vectors is linearly independent. Q says the set contains at most n vectors in Rn. And our theorem might say if P then Q. So if a set of vectors is linearly independent, then it contains at most n vectors in Rn. The contrapositive of this, if not Q then not P, reads if a set contains more than n vectors, that's the not Q. So the negation of having at most n would be containing more than n, then it is linearly dependent. And depending on your comfort level with all of this terminology and these definitions and your understanding of linear dependence or independence, it may be much easier for you to prove the contrapositive form versus the sort of original form. But since they are logically equivalent, it is still a valid proof. Some other important equivalences, we're not going to draw the truth tables for every single one of these, but you're, welcome to kind of do that as proof that these are equivalences. If P then Q is equivalent to if not P or, excuse me, is equivalent, if P then Q is equivalent to not P or Q, we're going to see it. That actually is going to lead to another common proof technique. We'll see that in a future video. The negation of negation P, so not P, is equivalent to P. And then we have what are called De Morgan's laws. These allow us to sort of distribute negation over and or an or. So the negation of P and Q is negation P or negation Q. And then negation P or Q is negation P and negation Q. So you can't sort of directly distribute, you distribute, but then your kind of, and becomes an or the or becomes an and. And again, you could go through the truth tables to show these are logically equivalent. I also recommend sort of playing around with some statements to, make sense of why this is true.